Today, we will have a discussion on the modern control strategies of a modern blast furnace. Today, we will explore the critical operational and design consideration for sustainable iron making. This journey will cover innovative fuel injection, precise thermal control, advanced gas and body management, strategies for hearth longevity and cutting edge process optimization. Our focus is on data and technologies driving the future of blast furnace operation. Now, coming to our next slide, which is more focused on the pulverized coal injection and oxygen enrichment, which are vital for reducing coke rates and boosting productivity. In recent experiments, PC particles groups were photographed by a high-speed cameras at 5000 frames per second with an exposure time of 2.5 microseconds. These experiments highlight critical parameters: gas velocity in blowpipe at 82 meter per second, a gas temperature of 1200 degree Celsius, and a PC injection rate of 200 kilograms per ton of hot metal. Other trials shows PCR values around 203 kg per ton hot metal. The goal alongside oxygen enrichment is to sustain optimal raceway flame temperatures. However, increasing PC rates often require adjusting Boden distribution to inhibit gas flow near periphery, as observed when PC rate increases. Modern bellless top systems are designed to allow high coal injection rates and controlled gas flow. Now, coming to our next slide, which is about maintaining a stable raceway flame temperature, which is very important during course of pulverized coal injection as well as oxygen enrichment. So raft is paramount important index. It's the critical temperature of the gas leaving the raceway, impacting modern iron and molten iron and slag quality. This temperature must be hot enough for the 1500 degree centigrade molten product, but not so hot as to melt raw material prematurely, which would disrupt body and descent, that we also see in cases when excessive flame temperature create a problem of asymmetric or body and descent in blast furnace. Operators now rely on automatic calculation of Tuyere flame temperature using data from the bottom segment analysis with a multiple injectant. Tuyere cameras are becoming a standard, offering real-time continuous monitoring from control room. This immediate feedback helps detect Tuyere blockages or lance damage, preventing costly blowpipe burn down. So some systems even use image analysis for automatic coal injection shut off when blockages are detected, or simpler robust system like light meters or differential pressures. So while tuyeres are usually installed horizontally, modeling tests have been indicated that raising them a few degree could shrink the raceways. Now coming to our next slide, which is very important and which is about a effective top gas management. And as all we know that effective top gas management is extremely crucial, especially concerning CO2 emission and carbon capture. So beyond standard top gas temperature, which typically ranges from 100 to 200 degrees centigrade, the industry is heavily invested in carbon capture storage technologies. Research explore anti-agglomerant screening in tubular reactors with specific tests conducted at 275 Kelvin using 30 milliliters of zero point 0.5 mole per liter TBAB aqueous solution. Pulverized activated carbons or PACs are studied for CO2 capture, demonstrating varied properties. For instance, PAC zero point 0.4 exhibit a total surface area of 404 and a total pore volume of 312. CO2 separation efficiency has been evaluated using material like PCN17 in dynamic breakthrough tests. For example, using a 14/3/82 volume percent mixture of CO2 S2O nitrogen at 25 degrees centigrade followed by argon purge regeneration at 50 degrees centigrade. For NOx reduction, ammonia injection system SCR are optimized. The ammonia injection amount is calculated based on flue gas velocity and NOx concentration with adjustment made until the coefficient of variation of outlet NOx is less than 20%. Notably, ammonia slip decreases rapidly increasing temperature and energy is completely consumed between 1200 degree and 1300 Kelvin. The steel industry is also increasingly looking towards hydrogen production as a decarbonizing strategy. Coming to our next slide, which is basically on the precise body and distribution which directly impact gas flow. Descent stability, it also take a control of efficient heat and mass transfer within the furnace. Now, ballast stop charging programs are complex and require detailed modeling. This includes measuring material falling curves, traditionally by filming material trajectory against a fixed grid, and more recently using laser nets to observe falling angles. The BLT's capability to lay down materials anywhere on the stock line is critical. Probes and other instrumentation are essential for tracking distribution effectiveness. A smooth body descent necessitates maintaining a pressure drop of less than 160 kilopascals. Computational flow dynamics simulations, that is the CFD simulations, are employed to quantify the impaction efficiency of fly ash particle on tube bundles in combustion system. These simulations often simplify the tube bundles to 2D cases to manage computational cost using a tube diameter of 40 millimeter, a surface temperature of 873 Kelvin, and a flue gas at 1300 Kelvin with 8 volume percent oxygen. Impaction efficiency has been studied at various conditions such as for S1 by D is equal to 6 or S1 by D is equal to 1.5 with particle velocity of 2 to 10 meter per second. Detailed multi-ring body distribution calculation programs use parameters like distributing chute rotating speed of 0.15 revolution per second, that is 0.15 revolution per second, a measured stock line depth of 1.2 meters, a Bourdon coefficient of 0.9 and a particle size of 50 millimeters. So the friction coefficient of the distributing chute can even be inversely calculated from the actual landing point measurement. Now coming to our next slide, which is about a very important aspects of modern blast furnaces operation and maintenance, that is about ensuring hearth longevity and effective slag management, which is a fundamental for long campaign lives with modern furnace targeting 20 years. Slag primarily role is to absorb gangue minerals, ash from the fuel and remove alkali compounds and sulfur. Optimal slag properties include a liquidus temperature below 14-15 degrees centigrade and a viscosity between 0.2 and 0.5 Pascal seconds. Cast tracking chart provide a 24-hour overview of casting operations, immediately highlighting slag delays or back-to-back casting, crucial for 2700 cubic meter blast furnace with a 2 taphole as shown in something nearly March data about which we are talking. Slag composition is critical, especially quaternary basicity has a great influence on slag viscosity with a sharp increase when R4 exceed 1.1. The hot structure is meticulously designed and monitored for heat transmission. Creep deformation of a Copper stay particularly when cycling between high and low head loads like 1050 kilowatt per square meter is a critical factor influencing deformation. This creep combined with the thermal cycling is a suspected cause of cracking in stave hot faces. Now, finally, process optimization and predicting modeling are the integrating advanced computational methods to achieve a specific goal, whether it is a lowest cost, least coke consumption, or minimal carbon emission. Computational fluid dynamics CFD simulations are critical, as we have already discussed in the preceding discussion. For 3D large AD simulation, that is LES, that is a large AD simulation LES, grid sizes are often 1 to 2 millimeters within a total of nearly 840,000 cells and a time step of 0.005 second. It is shown to be better simulate peak values compared to RANS modeling. The a flash chain mechanism is a powerful tool for process simulation, quantifying impact of coal quality and operating condition without the need for adjustable parameters for tar yield. It accurately predict ultimately we can say ultimate weight loss and gross partitioning into gas, tar and car within measurement uncertainties. Numerical models for equipment like external heat exchanger often simplify geometry, for instance using 1 by 16th of real EHE size with 6 lakhs grids, 600,000 grids to optimize simulation periods. Long and short memory neural network models are being deployed to optimize operational modes such as burner switching to decrease overall NOx concentration. The heat transfer coefficient increase linearly with solid flow rate. Even in coal bed methane applications, power law decline model predict gas production where exponent n is typically between 0 and 1, and looking forward, PEM electrolyzer for hydrogen production can achieve cold start to full power in less than 10 seconds and operate dynamically from 0% to 100% load with a temporary peak up to 300%. These are the key for reducing cost, improving efficiency beyond 80% and extending lifetime to at least 50,000 hours. 50,000 hours. So we can say in a closing that from micro scale fluid dynamics to macro level processes control, these insights demonstrate the relentless pursuit of efficiency and sustainability in blast furnace iron making. The integration of advanced diagnostic, computational modeling and novel material technologies. That are the three: advanced diagnostic first, then second is computational modeling, and third is the novel material technologies. It's not just an evolution but revolution in steel, in green steel production.